Welcome back to my YouTube channel. So, in the previous video, we saw how the orthogonality condition is being used in the Fourier transformation. So, just to recap, let's take an input vector of some size, and it has some real, or it could be complex as well. And if we take the Fourier transformation, since the data is discrete, we are taking the DFT of it. We would get a vector of the same size, and so the non-zero values would correspond to the frequencies at which, or the frequencies of our input signal. So since we have two non-zero values, we are assuming our input signal has two frequency content. So this is what we saw in the output vector. We get zeros. It's because we are satisfying the orthogonality condition, and we are getting non-zeros like C1 and C2 because of not satisfying the orthogonality condition. So if I write the equation of Fourier transformation, this is our input data, and this is the transformed data. So when we are iterating over the k variable, we are changing this term. K is going from 0, 1, 2, 3. So iterating the k variable means we are changing the frequency content of this term, which can be written as cos I theta plus sin theta. So what it means is, for some particular values of k, we would get non-zero values, non-zero response, and at this values of k, we would try to extract the frequencies of our input signal using the orthogonality check. So what I mean is, if this is our y-axis data, the x-axis, since we are iterating over the k variable, k equal to 0, k equal to 1, k equal to 2, and so on, this nothing but changes the frequency content of this term, and when the non-zero value corresponds to a particular value of k, we can easily find out the frequency content of our signal. So now what we need to do is we need to map these values of k to the transformed values of the input data. That is what we will look in this video, and it is quite a straightforward task. So before going in detail, I would expect you to get familiar with something called a sampling frequency, and my quest Diffraction theorem. Yeah, that's it for now. Please go through the internet and have a check. What does it mean? What does sampling frequency mean? But I'll give a very brief idea about it. Now, in the last video, I mentioned that our data, input data, could be a function of time or space or any other variable. But in this lecture, let's assume or let's consider our data is a function of time. So if this is my data, a pure harmonic function of one frequency, I'm assuming my independent variable, nothing but time, and this some data. So let's say it goes from t equal to 0 to t equal to 1 second. And since we are providing discrete data at some particular interval, let's take that interval of 0.01 second. So what I mean is I have discrete data like this, and interval of this data is nothing but 0.01 second. So total t is nothing but 1 second. And for this case, it is the same as time period of the input signal. Then delta t is 0.01 second, which is the time interval of the discrete data, what we are recording. So sampling frequency is nothing but 1 by delta t. For this case, it will 1.01 and it will come around 100 Hertz. Now, what it means is, now when we are doing a transformation, now based on what I explained earlier, when we are iterating over the k variable, it is nothing but we are iterating over the different frequency range. So automatically it means my independent variable in the transformed plane is nothing but frequency. So the x-axis scale for this is frequency. So the sampling frequency would determine my max value of the scale. So if you are interested for 1000 Hertz, you need to sample the data at 0.001 second. So based on your frequency range of interest, one needs to make sure the sampling rate of the input data, because it is not possible to retrieve the higher frequency range if the sampling frequency range has been done at a lower rate. So this is a very critical aspect. Now, similar to our time data, we will have something called as delta f, frequency resolution, and it is quite easy. There are different approaches. One straightforward approach is, all you do is sampling frequency by total number of data, because as I discussed it earlier, if my input data has the size of n, my output would be of the same size. And if we are to plot on the same scale, all I need to do is divide the sampling frequency by the same number of data. So this would give me the sampling rate, frequency resolution of the data. So this is how we map the independent scale before and after the transformation. This is same approach can be adopted if the independent variable is a measure of length or something else. So this topic is clear. Now to explain one more topic, if I have a wave function like this, and if I'm recording the data at only 4 points, one is this, second is this, third is this, and fourth one is this. And if I were to plot it, we would get something like this, right? Because I have only 4 discrete points. So the concept what I want to explain is, in order to capture a sine wave, we would need at least 4 points to make it look like a harmonic function. So let's say instead of 4 points, if I tell you to draw the sine wave using only 2 points, is it possible? Let's try to see. If I say 2 equidistant points, it could be either this 2 or this 2. So if we use the first point, it would look something like this. Take the second one, it will look something like this. So it is not possible to plot a sine harmonic curve using 1, 2, or 3 points. So we would need adequate number of data points to capture this sine wave, in case if one is interested to find the correct amplitude as well as the frequency content of the signal. Now another way to explain it is so this term over here, I will write it down separately. Cos 2 pi k n. This is always normalized from 0 to close to 1. And this is going from 0 to n, that is total number of data. So no matter what your input data is, it is always scaled from 0 to 1, and the orthogonality condition is being checked for these frequency components. So what I mean is, if my input signal is like this and it is going from 0 to t, the Fourier transformation, it does everything for the normalized data 0 to 1, and it will return, since it is iterating for the k variable which is going from 0 to total n in the span of 1. So once we have this 0 to t, we need to rescale the transform data to our original data. only the independent variable. So the way we do it is, it's quite straightforward. We know that instead of 0 to 1, we want 0 to t as our independent variable. So this n by n, we will multiply by t. So it would go from 0 to t, right? Instead of 0 to 1. But if I change this term by a factor of t, I need to account this change in the k variable by dividing it. So that is what you would do after doing the transformation. So this total number of data, it would remain the same, capital N. So this one, we will divide by t, and this one also by t. So let's try to confirm this with an example. If I have data of 0 to 100 seconds in a span of 1 second, the transformed independent should be something like 0 to 1 with a delta f of 0.01 frequency scale. Now if we use all this logic, let's see whether it is true or not. Let's start from 0. Now capital N is nothing but 100 by 1, which will come as 100 data points. So 100 divided by t. What is t? T is nothing but 100 seconds. So this is done. This is nothing but 1. Okay, this is correct. Now for delta f, it always will be 1, and 1 divided by t is 100, and it is only 0.01. This is the same as this one. So this is another way to build the frequency scale. There could be some other explanation for it as well, but this is a very basic thing. Usually people would not go in this detail to explain this topic because it is quite straightforward to build the frequency scale from a time scale. All you need to do is use the inverse relationship between time and frequency. But what I explained it over here is it may not be required, but hope it will help few of you people. So I think that's enough for this video. The next video would be the last video on this topic, in which I will try to cover the mirroring image and how to account for it in the algorithm. I'll also try to explain why it occurs, the mathematical explanation for it. Yeah. So have a great day ahead. Bye bye.